Hello everyone. As mentioned in the overview lecture previously, we are first going to discuss the beam theory as it pertains only to the lateral loading which induces simply and only the bending of beams. Okay, so the as per our overview again, what we are going to do is uh, first of all consider the principle of stationary potential energy, develop our theory, and then go on to the principle of virtual work. So first of all, based on the principle of stationary potential energy. Okay, so uh, let me draw the beam here. Please note that I am drawing these kinds of jagged ends here, meaning to signify that I am right now not interested in the specific kinds of boundary conditions which may be present at the actual ends of the beams. They can be clamped, they can be simply supported, it does not matter right now. And this statement that it does not matter right now, it is directly connected with the general nature of the theory which we are trying to derive here. So let me set it out very clearly at the very beginning that our objective here, when we say that we wish to find out or we wish to develop the beam theory, it is our goal, our final goal, to develop an equation for the deflection of the beam, a governing equation together with the set of appropriate boundary conditions for the deflection of the beam. Because once we know the deflections, we know the material behavior, we know the geometrical aspects, we can find out the strains, we can find out the stresses, everything. Okay, so since our theory will be general enough, it should be able to capture various kinds of boundary conditions. So right now we do not have to specifically mention which boundary condition this is about. When we go now, when you address specific problems, then uh, uh, you can specialize the general theory to that particular boundary condition. Okay, so in a similar fashion, our load, the lateral load, will also be general enough. So it need not be uniformly distributed. So that's what I'm representing here. Some general kind of distribution of the load. I hope you get the idea. All right, but please note that there is no axial loading here. Now, because we wish to proceed by the principle of stationary potential energy, let me write down the expression of the potential energy at the very outset. So this pi, the capital pi, this is equal to the V internal plus V external. And V internal we have seen earlier in our previous chapter while dealing with the Castigliono's theorem of deflection, that this V internal, the potential energy, equivalently the strain energy, this can be written uh, for the case of beams in this fashion. Now I have suddenly written this statement, okay, I have suddenly written down this formula, but there is a lot of backstory behind it. So I strongly advise you that if you are not too confident with what just went on here from this jump of this potential energy to this strain energy expression, I strongly advise you to please go back to the appropriate portion or the appropriate video from the previous chapter and take a look there. There will be a couple of other comments to make also, which I'll make subsequently. For the external potential energy, this can be directly connected to the work done by this external distribution of forces. So please note that this this loading, it is generally given by this q, which can be a function of x, and uh, the work done over a little elemental length of the beam is this qw dx, and that is integrated over the entire length of the beam. Now this is the work done. What we have to actually write down, or what we're actually interested in, is to write down the expression for the uh, V external, or the external potential energy. So all that you have to do is to write this with a negative sign. Okay, so uh, what do we do with this now? So we have to use the principle of stationary potential energy. So so all that we need to do is to apply this thing, which means that we are basically going to start our work from here. The first variation of that entire expression that we had written earlier is equal to 0. So this basically is the first line of our application of the principle of stationary potential energy. Now let us try uh, to move our attention back to our original goal. As I had mentioned, our final goal here is to find a governing equation for the deflection of the beam. This W, you note, it does indeed represent the deflection. Okay, so please note that W here is the deflection of the beam. So deflection means that how much uh, this beam is going to deflect from this straight orientation. Okay, so when it curves down like that, how much is the deflection uh, from that horizontal orientation? And that, you understand, will be very much a function of x. I have made a slight mistake here. This delta should not come here, that will come later. So this is right now just like this, and this dx is also inside. Sorry about that. Okay, so write that down better. Okay, that's better now. Now we do have the presence of this deflection here, so that gives us some hope that we should be able to obtain some kind of an equation involving the W. But what about this expression? This is expressed in terms of this Young's modulus. This I here is the second moment of area, or the moment of inertia, and M here is the bending moment. So there is no sign of the W right now. So this is the part where we have to use our knowledge from our undergraduate studies. So what we are going to use here is this well-known formula, uh, which especially the people who have had a wonderful gate preparation should have at their fingertips. So this M is the bending moment. This E and I are the same E and I that are present here. This R here is the radius of curvature, and we have actually discussed this in connection with solving problems based on the Castigliono's theorem on deflections in the previous chapter. So this M is basically EI by R. Okay, now this R here, this radius of curvature, the radius of curvature here, it can be written down in terms of the deflection like this. So what I have done here is to basically write down the deflection here in the radius of curvature here in terms of the derivatives of the deflection. And please note that when I do this, I am not appealing to any knowledge from from our undergraduate studies of beams or mechanics of solids. I am not at all appealing to that kind of thing. Rather, what I'm appealing to here, or what I'm using here, is our knowledge from uh, from our first year engineering mathematics curriculum. Okay, so when we study the various kinds of curves uh, and and the representation of the curvature uh, uh, based on the first and second derivatives, we do come up with this kind of formula there, and it is that exact formula. You can actually refer back to any of the standard textbooks of engineering mathematics. This is at least here at IIT Kharagpur, it is taught in our first year itself, and I'm sure in many colleges also it is taught in the first year. So I sincerely request you to take a look back at that if you don't remember this. Okay. Now, what we are going to do is we are going to make the approximation that this is approximately equal to d squared w dx squared, where we are basically saying that the slope dw dx here is not too large. Okay, so this basically works under the assumption that uh, dw dx, this magnitude, is much less than 1. All right, so uh, what we can do here is this m can be replaced by this ei by r, so that what we have here is this half ei 1 by r squared dx, and in the subsequent step we can replace uh, this 1 by r uh, by this d squared w dx square. Okay, and that's exactly what we are going to do. Okay, so let me go to the next slide and carry out the steps. But before we do any of that, I want to emphasize on something extremely important. You please note that when we are proceeding in this fashion, when we have written down this expression, when we are using these formulae, uh, we are implicitly basing our derivation and our theoretical development on the Euler-Bernoulli beam hypothesis on the one hand, as well as on the linear elastic material behavior on the other hand. Okay, so inherent in all of these derivations is the Euler-Bernoulli beam hypothesis. Let me write down here. Okay, so we are very much working under the assumptions of the Euler-Bernoulli beam hypothesis, which we all study in our undergraduate mechanics of solids. Euler-Bernoulli beam hypothesis, as well as we are using this linear elastic material behavior. So when I say Euler-Bernoulli beam hypothesis, what I basically mean is the kind of assumptions where we say that when a beam is bending, the plane sections, they remain plane and undeformed, as well as the assumption that the plane section remains perpendicular to the longitudinal axis of the beam. Okay, so it is those kinds of simplifying assumptions that all of this theory is based on. Furthermore, uh, these kinds of relations, this mr is equal to ei, it is very much dependent on the use of the linear elastic material behavior. Okay, so as we have seen in one of the problems of where we used a nonlinear material behavior in Castiglione's theorem on deflections, you saw that the connection between this this relation mr equal to ei is no longer valid. We do end up with a different kind of formula. Okay, so it is very much linear elastic material behavior here. Okay, so despite these restrictive assumptions, you'll see that this kind of a theory is very much applicable to a large number of typical engineering situations, which is why it is still popular and not just uh, as a simple fundamental teaching tool. Okay, so without any further discussion, let me get into the thick of things of these derivations. We will proceed from this line. So let me actually copy this thing and proceed from there. I'll copy this part and then move on. Sorry about that. My writing app sometimes just misbehaves. Okay, copy this and I'll proceed from here. So first of all, I considered the replacement of this 1 by r by this d squared w dx square of that, because this is 1 by r square, this dx, and then we have this term. All right, now we carry out the simplifications involving the first variation. So let me write down the steps. I hope you should be able to follow it. I'll do it step by step. So this half ei remains as it is. We carry out the first variation over this term. This is giving us twice d squared w dx squared, and then d squared delta w dx squared. So you please note that when I'm writing this, I'm basically making one jump of a step in going from delta of d squared w dx squared to this d squared delta w dx squared. So I hope it won't be any problem. In a similar fashion, for this second term, we don't have to worry about the variability of this q because that is given to us. It is the first variation of the deflection which we're interested in. All right, so this first term, it's like this. So from now on, whatever we do is just some mathematical tricks. And the good thing is that we really wanted to get to the stage where we could apply some mathematical tricks without having to worry at every step about our understanding of mechanics of solids. So we want to proceed in a very algorithmic, systematic fashion to obtain our governing equations and boundary conditions. And this is the part where this is basically just calculus of variations. Okay, so this is the full-fledged application of what we studied in our first chapter. Now there's the only motivation here that this term here involves the second derivative of the first variation of the deflection, while this is just the first variation of the deflection standing alone. Now what we would like to have is a term involving, so you see both of these are integrations from 0 to L, 0 to L. So what we would like to have is a term which does not involve any such derivatives, rather a term which only involves this first variation of delta W, just in the same fashion that we have the first variation of the delta W here, or the first variation of W here. Okay, you see there are no derivatives of this delta W. So we want to transform this term in a fashion such that these d square dx square, it disappears. So how can we do that? We have a mathematical machinery for that, and that is the integration by parts. So that's exactly what we are going to do. We carry out the integration by parts once to obtain a term like this. So these are the boundary terms. Minus integration 0 to L, and then we have the ddx of EI. So what we have done here basically is we have considered this EI d square W dx squared to be the 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 first term in the integration by parts, and this is the second term. So in the boundary term, it is this thing which gets integrated, and in the integration term, it is this term, this first one, which gets differentiated, okay, along with the integration of this second term also. So we have this. So as a result of this integration by parts once, what we have ended up is one step closer to what we wanted. What we want is this kind of a term like delta W here also. So we are one step closer. So earlier we had the second derivative involving the first variation of W. Now we have the first variation of the delta W. So if we can do another integration by parts, then we should be absolutely be left with a term which does involve this delta W without any derivatives. So we'll do that again. This boundary term remains as it is. So we are going to carry out another integration by parts, where again we're going to consider this as our first term and this as the second term. So this is going to be I'll also carry out another simplification here by considering that this EI here is a constant, so that I can take that out of the integration, out of this differentiation. So this is EI d cube W dx cube. Then I have this delta W because I'm carrying out one integration over the second term only. These now also get become the boundary terms. And now you note that because this is a minus, it becomes a minus, but there will be another minus. So this minus and a minus becomes a plus. And for this integration term, what we'll be left with is this ddx of EI d cube W dx cube. Okay, so just like we had done the ddx of that first term, which is present here, we have the ddx of this first term which is present here. Okay, and of course we have this delta W present here. So now we are set. You see, in both the integration terms that we have present, we have achieved our goal of obtaining a term which involves this delta W without any derivatives. Here also there is no derivative, here also there is no derivative. So we can club these two integration terms together, and what we are left with here is just the boundary terms. Okay, so let me write this again in the next page. So I have, let me take a look back. I have this term EI d square W dx square. Then I have this d delta W dx. Proper limits minus EI d cube W dx cube. We take a look back. I'm just left with this delta W. And then I have this 0 to L. So I'm going to club this this term and this term here. So again I'm going to take this ei out of this differentiation, so I'll be left with ei d4w dx is 4, sorry, x4 minus q multiplied, this whole thing multiplied by delta w dx, and you can take a look that this is indeed so. Okay, so this ei d4w dx is 4, and this minus q, and this entire thing gets multiplied by this delta w. So this thing is equal to 0. Now using our knowledge from the calculus of variations chapter, we can conclude that our governing equation is going to be the coefficient of this delta w term. Okay, so this is exactly the kind of thing which we did while obtaining the Euler-Lagrange equation. So this governing equation that we're going to write here, this is the Euler-Lagrange equation for this particular mechanical system under concern. So our governing equation will be the coefficient of this delta w term here, which is nothing but ei d4w dx is 4 minus q is equal to 0, and for the boundary conditions all that we have to do is deal with these boundary terms. So what we say is that we consider this term first, and then we consider this term second. So what we're going to say is that at x equal to 0 and x equal to L, you must be very careful in writing this thing properly. Okay, so at x equal to 0 and at x equal to L, what we have is that either we have this thing to be equal to 0, either ei d square w dx square is equal to 0, or, and this is very very important to write properly, or this dw dx is specified. What we mean by that is, what we are actually thinking is like this, that ei d square w dx square is equal to 0, or this entire thing, this d delta w dx equal to 0. Now d delta w dx equal to 0 is like delta of dw dx equal to 0. Now that basically means that if the first variation of anything is equal to 0, it must be so that that thing of which we are taking the first variation, that is a given to us. Okay, so so what we are writing here is that our dw dx, we are not going to say that dw dx is equal to 0. Rather, it is extremely important to write that dw dx is something which is specified to us. It is specified, it need not be 0. Okay, because all that we need to ensure is that the first variation, the delta of dw dx, which is of course equal to d delta w dx, which is present here, the delta, the first variation of this dw dx is equal to 0, and that first variation of dw dx will be equal to 0 if dw dx is actually specified to us, because if it is specified, then there is no question of its variability, which means that the first variation of that has to be equal to 0, which is all that we need here. Okay, so that is quite a mouthful to say, but it is extremely important to write this down properly. In a similar fashion, again we go to this term and write this. Again, at x equal to 0 and x equal to L, we have either this first part ei d cube w dx cube, that is equal to 0, or w is specified to us. Again, in the same fashion that we had discussed the 0 here, here also we should not be suddenly writing that w is equal to 0. Rather, we should be very careful in saying that it is w which is just specified to us, because if it is specified to us, then the first variation of that is of course going to be equal to 0. Okay, so this is our governing equation, and these two statements, they together make up our boundary conditions. And please note that these boundary conditions have come up to us in the form of this either or statements, because back when we were discussing our statement of the problem, or this general schematic of our problem, we had not actually specialized to any particular boundary condition. We had left it as it is. Okay, so this could be simply supported, this could be clamped, anything. Okay, it could be free. So just take a look at what we have managed to obtain here. So suppose indeed that at x equal to 0, we have uh, the end as clamped. If it is clamped, then the deflection of that is prevented. If the deflection of that is prevented, you note that what is basically going on is that the w is specified there, and this is the part where it will be which is what is going to be applied. So if the end is clamped at x equal to 0, what we're going to say is that at x equal to 0, this w is specified, and if this w is specified, then you cannot say that at x equal to 0 this is true. Okay, so either one of these has to be applied. Similarly, if the end x equal to L is also clamped, then again you have to say that w is specified at x equal to L, which means that at x equal to L you can no longer say anything about this. So that is the significance of this either or statement. At a particular end or at a particular boundary, once you zero in on a particular, or once you hone in on a particular uh, option of this, okay, the other option automatically gets deleted from your consideration. Similarly, for the clamped end, we know that the slope is basically specified to us, which means that this dw dx is specified to us. So again, for that clamped end, what we'll have is that at x equal to 0 and at x equal to L, the dw dx is specified to us. Okay, which automatically means that at both x equal to 0 and x equal to L, this other condition that automatically need not be considered. All right. Again, alternatively, suppose we have at x equal to 0 a simply supported end, which means that at that end there is no restriction regarding the slope, uh, which means that dw dx is not specified to us. If it is not specified to us, then it is the other one which is going to get applied. So for a simply supported end, we have this ei d square w dx square equal to 0, and you understand what that means. Okay, so ei d square w dx square, it basically is, so you see this is what ei 1 by r, so this is like the moment. Okay, so ei 1 by r, this is the moment, so moment is equal to 0, and that is exactly true for a simply supported end. Again, let's say at x equal to L, you have a free end. So if it is a free end, then certainly our w is not specified. So if it is not specified, then this simply does not get applied. Rather, this gets applied. And what is this? This, from our undergraduate knowledge, is nothing but the shear force at that end at x equal to L. So overall, you see, as a combination of this x equal to 0 and x equal to L, both here and here, what we must end up for every beam problem is a set of 4 boundary conditions. Okay, so at x equal to 0, you have two conditions from these two statements, and at x equal to L, you have 2 conditions from these 2 statements. So both of them will get applied at both the ends. In total, you have 4 conditions, and that must be so that we do end up with 4 boundary conditions, because our governing equation is a 4th order ordinary differential equation involving the w. So if you do manage to integrate this thing to obtain the solution, you will end up with 4 constants of integration. In order to obtain the values of those 4 constants of integration, you do need 4 boundary conditions. Okay, so overall, this is a nice, consistent, closed system of solution of equations to solve, and for particular problems, you can go ahead and find your solutions. So on that note, I will end this lecture. Thank you very much.